Okay, welcome to this short video on indices, or powers as they are also called. And we're going to use the rules of indices that are in this box here, and we're also going to first simplify these four expressions using those rules. Okay, now the first one is quite simple. We have a 5 and we have x to the 7 over x cubed. And if we look at this rule here, we can see that we need to subtract the powers to give us x to the 4. So the answer to the first one is quite simply 5x to the power 4. And there's not really any working out you can do to go with that one. Okay, likely just to be 1 mark in an exam question. Now the second one, we need to use the fact that a negative power is better converted into a positive power, okay? And to do that, we need to turn the fraction upside down. It's kind of shown here in this rule. All right, so I'm going to rewrite this as 3q cubed on the top, okay? And the denominator is going to be p squared q to the 5. Okay, p squared q to the power 5. And all of that is going to be raised to the power of 2. Okay, in other words, squared. So I'm going to put all that in a bracket like this and square it all. Okay, now if you follow the rules in this box here, okay, when we square something that's already had a power applied to it, we're just going to multiply the powers by the 2. Now remember, we've also got to square the 3, so that's 9, okay? The q cubed becomes q to the power 6. And on the denominator, we're going to have p to the 4 and q to the 10, okay? P to the 4 and q to the 10. Now, there's two things you could do now. The first thing is to look at the q to the 6 and the q to the 10, and that will leave you with q to the 4 on the bottom and q to the 0 on the top, which is just 1. So the next step from that is that equals 9 over p to the 4 q to the 4. Okay, now it may be convenient to leave it in that form, okay, or it may be better, depending on what the question's asking, for you to leave it as I'll just put or here, leave everything on one line and not have a fraction. In that case, it would be 9p to the minus 4 q to the minus 4. Okay, both of those two statements are equivalent. Okay, so I'm going to leave that one underlined because that's the one that I think you would go for first. All right, now the next one is concerning a multiplication where you have a base of n and a power as a fraction and another fraction. Okay, but we apply the same rule, and it's basically this one at the top here. All right, so we're adding together the two powers. So this is equal to n to a single power of negative 2/3, okay, plus 3/5. Okay, so that fractional bit at the top, all of that is a power of n. We don't necessarily need to put it in a bracket, but just make sure that it's elevated so it's shown as a power and not sitting on the same level as the n down here. Okay, if you want to make it clear, you could have put that in a bracket of its own if you wanted to, like that. Okay, now we just do a fraction addition in the normal way there. So we're going to change them both into 15ths, okay? And that's going to give me negative 10 15ths plus 9 15ths. Okay, and I can just put that as a single fraction over 15. Okay, like that. Again, making sure it's all up in the air, away from the n. And of course, that's going to give me n to the power of negative 1/15. Okay, and that's the answer. You could use this rule and write that as 1 over n to the power of a 15th. Because it's only got a 1 on the top, what's even better is to put the whole of the 1 over n to the power of 1/15, like this. Okay? But just be careful with that, because that only works if the top is, if the numerator is a 1. Okay? But that's it, and that's the answer. Anything to the power 0 for this fourth one here is 1. Okay? So it could be an algebraic expression, it could be just a number, it could be a fraction, but if it's to the power 0, the answer's 1. The only exception to that is that this bracket can't equal 0, because 0 to the power of 0 is undefined mathematically. Okay, so if you were given this expression, you will probably find it will tell you that x cannot equal 0. Okay, like that somewhere, because it couldn't be 0 for that to be true. But whatever it is, as long as it's not 0, anything to the power 0 is 1. Okay, now on this side here we have an equation to solve, an unusual equation, and the unknown is contained in the power of both sides. Now, before you can even begin to do that, you've got to look for some similarity between the number here, the base, which is 3, and the base here, which is 9. And you've got to try and rewrite one in the form of the other. Well, the 9, of course, is 3 squared. So this whole equation can be rewritten as 3 to the power x plus 1 is equal to 3 squared, okay, to the power of 2x minus 5. And once you've done that, you can start applying the rules of indices. And the one I'm going to be using is this one here, okay, because the next line from that would be 3 to the x plus 1 is equal to, timesing this power here by the 2. It's equal to 3 to the power of 4x minus 10. Okay, and now that I've created an equation where each side is 3 to the power of something, I can remove the 3's, because it logically follows that x plus 1 must equal 4x minus 10. And suddenly I'm left with a simple linear equation to solve. Okay, now I could just, let's take x from the right. So I get 1 equals 3x minus 10. So I've taken x from both sides. Add the 10 to both sides. 11 equals 3x. So therefore, x must be 11 over 3, 11 thirds. Okay, and that's the answer. So I hope that's been helpful, and make sure you learn these rules and know how to apply them. And be very careful when you're writing powers and indices to show the base down on the line below and the power up in the air clearly separated on a different level, okay, because it can be very confusing if the powers end up being level with the base. Okay, so I hope that was helpful. Take care.